Let's continue to take a look at estimating the area under a curve using Riemann sums. We've already done this problem where we estimated the area under the curve f of x is equal to 16 minus x squared on the interval from 0 to 4 with 4 subintervals. Just as a refresher, how we do that is we subdivide that interval on the x-axis from 0 to 4 into 4 subintervals, like I've done here. Then I'm going to draw a rectangle from the left side of each interval. So my first interval goes from 0 to 1. I'm going to take the left side of that and draw a rectangle. Then I'll do it again on the next interval from 1 to 2. Start at the left side and draw a rectangle. From 2 over to 3 and finish up with 3 over to 4. So there we go. In order to estimate the area, we're going to take the sum of these left end rectangles. Each rectangle has the same base. I call that delta x, being a base of 1. And then we'll just go base times height. Well, base times all of the heights. So the first height is actually the functional value at 0, the left end of the first subinterval. Then we move on to the second one. That would be f of 1. And f of 2, and finish at f of 3. Notice that we don't finish at f of 4 because the left end of the last rectangle ends at 3. Anyway, now we go and actually find all those values. F of 0 is 16, f of 1 is 15, f of 2 is 12, and f of 3 is 7. We add that all up, and we estimate the area to be 50. Now, another important question is, how accurate is that? Would you expect the area underneath that curve to be bigger than 50 or smaller than 50? And I notice, in looking at the picture, is that as far as my rectangle goes, there's always this little bit extra that's always hanging over the curve on each one of my rectangles. That would lead me to believe that this 50 is more than the actual area. So naturally, another way to estimate that area could be using the right end sums. So with the same function on the same interval and the same number of subintervals, I want to draw my rectangles this time starting from the right side of each subinterval. So then from 1 to 2, I would start at the 2. From 2 to 3, I'd start at the 3. And from 3 to 4, I start at the 4. And I'm going to find the area of all these rectangles and add them all together. Again, I notice that the base of each rectangle is the same. That delta x is still 1. But the sum from the right ends is going to be the base times each of the heights. Recognize that the first height is not the functional value at 0, but the functional value at 1. And then we go to 2, 3, and this time we do finish up at 4. Finding those values, f of 1 is 15, f of 2 is 12, f of 3 is 7, and our last one, f of 4, is actually 0. And when you look at that last rectangle, you see why it does have an area of 0. There's no height to it. So we finish this up by, finishing the calculations. Looks like 19 plus 15 is 34. So now we've come up with an estimate of 34, where the last time it was 50. I wouldn't expect this one to be any more accurate, but I do want to recognize that when I draw from the right side, there's this little bit of area that is not getting counted for each rectangle, right, which is going to make me believe that the actual area under the curve is greater than 34, but still smaller than that 50. Of course, we're going to continue with this idea and try and find ways to make this estimate more and more accurate, even to the point of being exact. So let's practice finding some left-hand sums on some different functions. Here I got the function f of x is equal to x squared plus 1 on the interval from 0 to 3, and we want to do it with 3 subintervals. So the first thing that you should do is subdivide your interval from 0 to 3 into your 3 subintervals. And we are going to draw our rectangles from the right side of each interval. Now find the area of all those rectangles. Recognize that the base of each rectangle, delta x, is still 1. So the sum of all the right ends is going to be 1 times f of, well, on my first interval I'm going from 0 to 1. The right side is 1. That's where I'm going to start. I only have to find 3 of them. So 1, 2, and 3. Now we're actually going to have to calculate those functional values. F of 1, we take 1 and plug it into f over here. 1 squared plus 1 is 2. 2 squared plus 1 is 5. And 3 squared plus 1 is 10, making my estimate 17. I would expect this 17 to be an overestimate because within each rectangle, I'm always counting a little more area than what is under the curve. And we need to think about ways to be more accurate. One way we could be more accurate with this exact same function is to use more intervals. So now let's estimate that same area on the same interval for the same function, this time using 6 subintervals. So if I subdivided 0 to 3 on the integers 1, 2, and 3, that only gives me 3 subintervals. What we should do is just take each of them and split them in half. Now, draw our rectangles from the right side of each interval. In order to find the sum of the right ends, we're going to find the area of each of these rectangles and add them together. This time our delta x is not 1 because we took that distance of 1 and cut it in half. So now our delta x is 1/2. That's the base of each of those rectangles. To find the height, I'm going to take the functional value. But I'm not starting at 1. My first rectangle here, the x value is actually 1/2. And so I'm going to use 0.5 in there, or 1/2, however you want to look at it. And then I'll continue to 1, 1.5, 2, 2.5, and finish up at the right side of my last rectangle, and that is at 3. Now it's going to take some calculating to find all of these values. We do know some of them from the last problem, but all of these ones with the 0.5s in them, we're going to have to calculate. Like f of 0.5 is going to be at 1.25. F at 1 is still 2, but f at 1.5 is now 3.25. F at 2 is 5. F of 2.5 is 7.25. And we finish up with 3 squared plus 1, again being at 10. A little bit more calculating left to do. Adding up everything inside, I get 28.75. And then divide by 2 to get 14.375. We notice that our last estimate was 17. And this time I'm down to a little over 14. But still, this thing is an overestimate because with each rectangle, it looks like I'm still counting more area than what is under the curve. However, it is a better estimate because there's less that's getting wasted. So let's try one more just to be sure we got it. This time, we're going to use g of x is equal to the natural log of x on 1 to 3 with 4 subintervals. So the first thing to do is to draw in our 4 subintervals, and then our rectangles coming from the right end of each of those subintervals. We recognize that from 1 to 3 I got 2 in the middle, and so this must be 1.5 and 2.5. So my delta x, the base of each rectangle, is again a half. So the sum of all the right ends is going to be 1/2 times. And this time we start with g at the right end of our first interval at 1.5. And continue to 2 and 2.5 and finish up at the right side of our last rectangle, g of 3. This is going to take some calculating, and it's not really going to be pretty, so I'm going to do it real quick and just write all of my answers here. These are all of those individual natural logs, and now we have to add all them decimals up. I get 3.112 and finish off by dividing by 2. 556. And there's our estimate. Still recognize that this is an overestimate because I'm counting more area than what is under the curve.